We're ready for the second last talk conference. And so we have, let me say his name correctly, Patrick Heimbach. Is that good?
That's good. That's great.
Heimbach from University of Texas, Austin, who's going to talk about leveraging Hessian information for ocean observing system design.
Thank you, Larry. Thanks so much for inviting me to this, to this great workshop. I have to do two apologies. So the title is actually was in the program. I talked about this, and I did submit it again this time, but I thought in the context there was nothing neural in the 2021. It was a lot about derivative information Hessian, but I thought to bring in sort of this idea of how we use neural networks in ocean and climate modeling, I changed the topic and subject. So that's my first sort of apology. I'm an oceanographer, not a statistician, and I'm going to very much still use, maybe unlike a lot of the themes here, use physical domain knowledge in the form of physical ocean models in some of the estimation procedures that we're using adjoint methods. And because of that, so basically the title is sort of Differentiable Programming for Hybrid Data Assimilation and Machine Learning. I should maybe in the sort of given, present day, the times that we live in, before I start to slam climate models or sort of point out deficiencies, I should put out sort of that all models are wrong, but some are quite useful. Actually, I wanted to rephrase it a bit. I messed that up, but just wanted to sort of an early triumph of climate modeling. Here is a work by Suki Manabe, who won the co-recipient of the Nobel Prize in Physics 2021 from the NOAA Geophysical Fluid Dynamics Laboratory. One of the first climate model, very simplified climate, but still, sort of a GC, general circulation model. This is a half hemisphere, so from the equator to the poles here, conducted here in 1975, where they simulated this response of CO2 doubling and what it would look like in the surface atmosphere here from the surface to the top to the troposphere. And one thing that they predicted was sort of this amplified surface warming that would be stronger than the global mean in the Arctic. So that's something that we call polar, or actually specifically Arctic amplification of this climate change signal. Something that is now well observed in taking here the difference between 2020. Sort of a decadal mean of the last decade versus the decadal mean of the years 1980 to 1990. So it's really these models have been quite remarkably, even simple models. There's some large-scale robust features that have been predicted 50 basically years ago. And just fast forwarding to 2021, this is this Intergovernmental Panel on Climate Change, the 6th assessment report, a comparison between 1990 and 2021, all the things that we had no good estimates of, like the energy budget of the globe, what we call the sea level budget, meaning it's partitioned between thermosteric and halosteric on the one hand side, but then also barystatic. That means addition of mass, for example, from melting ice sheets. How is the global mean that we can measure now very well from satellite altimetry? How does it compose of the different components? And something that we now today think that with the more observations that we have, we can actually really understand how this budget comes together, and plus other things. But now, of course, there are problems remain with these models, and this is an example of something that was talked about earlier today that one should look at, of course, depending on what one does with it, with a level of suspicion. This is a multi-model ensemble mean. So exactly sort of the question, can we average sort of the different types of models that have their respective structural model errors, but let's not talk about this for now. Even if we took sort of the same model rendering in an ensemble for either perturbed parameters or initial conditions, the patterns basically have been fairly robust, and they have been robust across several generations of even IPCC reports. And this shows sea surface temperature of an annual mean, and you see these basically regions of large positive anomalies, large negatives anomalies. They are not randomly distributed. They have concrete patterns, and that points to missing dynamics or that sort of large scale dynamics that maybe is still not sufficiently well represented in these models. You see here the Gulf Stream, for example, that suggests something Gulf Stream sort of misplacement on where the Gulf Stream separates into the North Atlantic. Sort of similar here. The other sort of the Pacific's Gulf Stream, the Kuroshio current, sort of here these dipole patterns, and so on. So there are these remaining patterns of uncertainties that, of course, we want to understand better, reduce. And the general notion in the community is that parameterization of the subgrid scale of these models, be it in the atmosphere, like cloud physics, but in the ocean, which is sort of my domain, play an important role on how these processes are parameterized, and then also, of course, how these parameterizations are structurally designed and how, whether these parameters are calibrated. So an example here, we go from the large scale here in the ocean on the order of 100 kilometers and larger, and then we go here to what we call the mesoscale. So these are geostrophic eddies. So these are the ocean's sort of weather system, if you like. So they're on the scale between 10 and 200 kilometers. And then oftentimes, so early climate models basically resolve just these scales here. In the very latest renderings, some of the models, but still not all of them, even resolve sort of at the level of about 25 kilometers. But everything below that, all of these, what we call submesoscale processes, boundary layer processes, and so on, these are certainly not resolved. And so we need to parameterize these in the models. And so the question becomes, how do we, what are the functional forms of these parameterizations? How do we calibrate these uncertain parameters in the models? And that's really a deficiency because it's such a complex process that this has been, there's a lot of hand tuning or ad hoc tuning that's been going on in the modeling communities, whether it's just ocean only or even a climate modeling community. And so we have to, one of the first questions is, what type of data do we have in the ocean? And, the more general questions, I always like to raise this, is ocean science or oceanography a big data science? And certainly I would argue from an observational perspective, it's not at all, right? So we are totally data starved. We have maybe some good coverage of the surface properties now, doing a number of satellites measuring sea surface temperature, sea surface height, so altimetry, gravimetry, which is actually measures, so actually it's amazingly, it measures ocean bottom pressure changes. But even those have certain resolution. They have spatial temporal patterns that have some deficiencies. The minute we go into the water column, it becomes much more dire. We have Argo profiling floats, but they represent the footprint of 300 by 300 kilometers, measuring a profile every 10 days. We have these ships that go out to sea and lower these rosettes basically to the seafloor to measure hydrographic property, temperature, salinity, other traces in the ocean. But you can imagine, right? So how many of those super expensive ships are slow? You cannot take many of them. And sort of most exotically, recently, of the last maybe 10 years, elephant seals have been equipped with sort of instruments and telemetry. And they have been, so not by physical oceanographers, but it was more like by marine biologists who wanted to understand the foraging patterns of these animals. But of course, as physical oceanographers, we take advantage of these data because they do measure temperature and salinity. And whenever they complete a dive, basically they send their data to a satellite, which we can then take advantage of to get measurements here in the Southern Ocean in some of the regions where there is very, very little information or data because of the place, the remoteness of the place. So we have this sparse and heterogeneous observations. So that's one of the knowledge reservoirs, and we really think that we need to still rely on known physics and dynamics of the ocean in a process called data assimilation, and that's just one example of a global ocean data assimilation project that's been trying to use the combination of all of these observations from these different types of satellites, measuring different properties of the ocean, and then here what we call in situ measurements. Here, most prominently today, what's called the Argo profiling programs, around 4,000 of these profilers in the global ocean, measuring the top 2 kilometers of the water column, each of these profiles once every 10 days. And then basically this eclectic type of observing systems, we basically combine with an ocean general circulation model that basically solves an approximated form of the Navier-Stokes equation on the rotating sphere in what we call state and parameter estimation. And for this, we've been using, I'm not going to go into how we do this. It's not it's not a filtering-based approach, and I'm going to talk about why that's not the case. We'll basically use a smoother-based approach, so it's really like an inverse problem that we're solving using an adjoint of this ocean general circulation model. And what I would like to try is I'd like to also hijack a bit the notion of learning, right? So what do we mean when we talk about learning? The context here is basically them saying, okay, so we have our physical model that becomes our dynamical interpolator of all of the data. And blue here is you think of the dynamical core, and in green are all of these components of the model that have uncertainties, right? So we have these parameterization scheme that I've mentioned for geostrophic turbulence or other types of turbulence, vertical tracer mixing. We have initial conditions that are uncertain, right? So when we start to spin up a climate model from a state in, let's say, 1870 or whenever, right? So we don't know what the ocean looked like in 1870. There's uncertainties in those. There are boundary condition uncertainties, of course, there are also uncertainties in the numerics, the structural errors that I'm not going to talk about that much today. But so let's think about sort of this problem here. And so the first thing that maybe I would like to point out is that we can coming from an inversion perspective, right? So we would like to know if we had good observations of the ocean interior, so we can actually infer what are the uncertain boundary conditions. And air sea fluxes, we can't really measure fluxes. So oftentimes we deduce fluxes from measurements of the properties in the surface ocean and the surface atmosphere. And so this is a prominent example here. For example, we would like to infer air sea flux of CO2 that we would like to, for example, infer from interior measurements. This is a program called the SOCOM, and that Alison knows much more about it than I do, but it's the Southern Ocean Climate and Carbon Observation and Modeling project, a large project. They've been taking, again, Argo and floats equipped with biogeochemical sensors, and then measuring CO2 concentrations. But can we use sort of this? Can we invert for air sea fluxes? So this is one. So we've been learning the surface boundary conditions. The next problem is again the initial condition problem, and that basically is the classical filtering problem of optimal estimation and control, and that's of course what's used in numerical weather prediction, right? So we have we consider here on this plot the red curve. So we have a forecast of a model. So the model forecasts a certain state at a certain time. New observations come in, and then basically using Kalman filter and all of its variants, ensemble Kalman filter methods, we basically come up with a new initial condition that basically we think is the best. It's a weighted fit between the background, so the forecast, and then the new data that we have in order to find a new trajectory that basically provides sort of an optimal estimate of the forecast over a certain period of time. But the problem with this, so this is great. This works really well for numerical weather prediction. But what's for climate reconstruction, I already point out here. So these jumps are of course unphysical, right? So think about temperature at 1,000 meter depth, right? So when the model has a certain simulation, and then the data, for example, from the Argo profilers has another temperature, and then basically this analysis increment tells me I need to change my temperature at this level by a certain amount, which you can think of as an artificial source or sink in my conservation equations. And this happens basically every 6 hours or every 3 hours in the model, and it may mess up it will give us unphysical jumps in the solution. So on longer time scale, this filtering problem has also been used or attempted in what's called initialization for decadal prediction. So where you have here observation here in this is the black curve. You have a model that is when it is not properly initialized. So for example, the initial conditions are very bad, basically has this gray trajectory. And then the hope is that if you now have a good estimate of what the true ocean, for example, would be, you basically come up with this red curve here. But then if the model is not well calibrated, the model basically jumps back into this from its sort of the initialized state to this to its preferred state in what's called the initialization shock. And that's been a problem with trying to adopt these methods in models that are where you try to have a good initialization, but where you don't have still issues with not very well calibrated models. And so just to point out here is again the use for what we call, if we do reconstruction using these filtering methods, we get what's called reanalysis products. These are the products that ERA 5, right? So everybody who's read about the big advances in purely data-driven weather forecasting, then this is exactly the products that have been generated using data. So first of all, these are not observations; they are products which data assimilated products, and they have their quirks, right? So they also have their artifacts in their space and time variability that may come in purely from the data assimilation method as opposed to from real variability. So just as sort of a side note and a caveat. So the smoothing method is for reconstruction, for actually generating those reanalysis products, which is not what's typically used. So filtering methods is what in most cases is used today because it's easy. It uses Kalman filter methods and other. But so the smoother methods is really optimal. So it's the blue curve here where we try to fit the observations to some extent as good as we can using, for example, in our case, an adjoint method or using the RTS smoother approaches, which are not, again, widely used, but probably we think should be used for looking at sort of dynamical reconstruction and especially doing reconstructions where you try to use those states to do budget analysis, where you try to understand, in order from, if I change from the state from here to here, what is the dominant factor in my equations? Is it lateral advection that has led to, for example, the warming? Is it the surface heating or cooling that has led to a warming? Is it the diffusive processes? Is it changes in the circulation, sort of lateral advection changes that basically lead to this, right? So you really would like to, what we say, close budgets in order to be able to do this, and therefore you want to have state estimates that basically try to conform with the equations of motion. Now I'm coming to the sort of, of course, more after. This is where when we try to learn the parameters, these of for example, the subgrid scale parameterization. And here is so this is a hard problem, and it's been I think appreciated for quite a while because also it's a hard problem to solve. These parameters dimensions are very high dimensional. These climate models are very, very expensive to run. done. So again, sort of sampling methods are very difficult to do. The idea now recently has been sort of that what if we replaced one of these parameterization scheme, for example, by a neural network, right? And so there's been some really successful work. For example, and I'm constraining myself to the ocean. There's similar work, of course, and maybe more advanced even in the atmosphere. But here, this work by Laura Zanna in Bolton, who you probably know very well. So the idea here is basically, again, so you have your conservation equation, and then here for the mean, for the resolved flow, these are the bar quantities here, and then you have here the unresolved processes that come here in the divergence of a let's say a stress tensor here, or a tracer tensor that we try to learn, that we don't know. And we basically use a neural network, and the training data now, again, I've shown you, right? So we don't have good observational data, but at least for these types of problems, we could say, well, we can do sort of large eddy simulations or resolution at very high resolution that do resolve the mesoscale eddy field. And we train the neural network on these simulated data, and then we basically then plug those trained neural networks back into the model. So this is something that's sometimes been called offline learning or a priori learning. This is really nice, but of course what's been found is that there are different. Well, one of these training exercises will learn a certain type of missing physics, but there are many other processes in the model, like topographic mixing, and the influence of tide, the internal tide dissipation, conversion, all kinds of other processes, lee waves in the ocean that are not represented by many of these processes, right? And so the question then has become: can we learn these neural network architectures within the full model, right? So can we actually and can we also then, instead of just learning them on simulated, so we need to have these simulations, then we compute the statistics here of the eddy field, and that's what we then learn here. But we're not using, for example, there's no observations that go into actual observations into the training here. Whereas if we could train on the state of the model, the actual physical state, and if we could train the full model, then maybe we have an improved chance of basically getting a model that basically reduces the drift or biases in the model. That's basically the whole goal of why this exercise is done. And so this leads to this concept of full model or online or end-to-end learning, where basically we basically do a learning process that encompasses not just the neural network, but the entire model. And for that, we need the model to be, depending on which approaches we use. But again, if we use, for example, if we want to train these neural network weights, we would then also have to have a differentiable dynamical core of the model. And that's basically that's the story that I want to go at. And then of course the full end-to-end, sort of, this is the full extreme, is the full model is now replaced by neural network architecture where we have full, either weather or climate emulators. And the notion, I think, in our field today is that, I mean, it's actually still disputed, and things go very quickly, that this has been very successful, or is very successful for numerical weather prediction, where you can run these emulators for, let's say, 10 days, maybe they might even be successful now on the order of 30 days, or maybe begin to do seasonal prediction. But for climate, we think that for long-term simulations, for example, for climate, these are very hard. This is a very, very hard problem. We need to conserve energy. We're looking for signals. Oftentimes, our climate signals are very small residuals in a very noisy system, right? So we're looking, for example, the Earth energy imbalance is on the order of 1 watts per meter square in a system that has regionally on the order of plus minus exceeding 200 watts per meter square in, for example, ASC heat fluxes, and where we where we're really looking at and trying to find, basically, we and our climate models have to do a really good job at basically conserving energy and these properties in order to basically give us sort of long-term trends that we think are robust trends of the system. So basically, the reason why I brought this sort of these different concepts is that depending on, again, the method that you're using, a unifying conceptual tool here is for the physical models is the adjoint-based inversion, or for the neural networks is basically this how you train those is backpropagation, right? So, and which is basically also just an adjoint model, depending on how you name it, right? Because you basically compute the sensitivity of your loss function with respect to your weights using automatic differentiation. And the question is, can we basically combine these two approaches in order to basically do this full model of learning? And so this is basically this idea of what's become fashionable, sort of to call this, differentiable programming. So basically, we have the dynamical core of a physical model that is actually differentiable, and it's differentiable using automatic differentiation tool. And some of the people who have been doing automatic differentiation for many decades have been pointing out, look, it's just we've been doing this for decades. And in fact, I have actually been doing this for at least 2.5 decades. We have actually been working with a differentiable ocean model that's been written in Fortran for the last 2.5 decades to work on this adjoint-based state and parameter estimation using a global ocean general circulation model. But of course, there is no machine learning, no neural networks involved in these approaches. So when the revival of the idea of differentiable Earth system components was sort of happened in the last few years, right? So there's a paper that basically gives a review of what could we do if we had these differentiable Earth system models. And here another review paper and another one here, and then this paper by a group at Google and the ECMWF, that's the European Center for Medium Range Weather Forecasts. That's always when you say the European model, right? So when you hear about weather forecasts, well, what does the European model? That's that center. And they basically came out with this idea, where this is neural GCM for weather and climate. And I would contend that for weather, yes, for climate, there's still work to do, but they've basically exactly implemented this idea of combining a dynamical core. And so they actually rewrote the dynamical core of the GFDL's atmospheric model, the FV3 dynamical core. We wrote this in JAX. And that's basically the left part here, where you step through the dynamical core, but the physics parameterizations are now left to this what they call the learned physics. Basically, it's a neural network architecture that is basically trained on observations or on not observations, on data. And they're actually, like as many of these do, they train this on reanalysis data, but it's good enough, right? So again, but with the idea of having a model that is better, where at least the physics is better calibrated against the data that they have in order to reduce model biases and have sort of stable simulations. So this is for the atmosphere. So for the ocean, so actually we've been we would like to do something similar, but we've been working with a different ocean model that has been written in Julia. And so why Julia? The main reason is that we really wanted to leverage efforts that existed on the one hand side with this effort that's been going on now for maybe 7 years or so, the Climate Modeling Alliance, basically that consists of the complete rewrite of a new climate model in Julia, which consists of an atmosphere that's been taken on at Caltech, and then an ocean model component at MIT. And the idea is also part of the idea of basically this effort was to have better learned from observation, or actually from data. These again can be either observations or LES simulation. Then of course Julia, why this is, it's a language that basically can harness sort of next generation compute architectures much better. So efficient implementations on GPUs, on TPUs, and I'm going to show some early results on this in the next few slides. So we've been working with what some people know is this ocean component of Klima as the oceananigans.jl. So this is the first paper that came out with some idealized simulations of oceananigans for both hydrostatic and non-hydrostatic simulations, and then which has this, in terms of its numerics, it's not that much different from conventional ocean general circulation models, but there's some really advantages on how basically those models, this implementation can harness GPU kernels. And this is basically a recent paper that basically shows sort of early simulations with this oceananigans model at 1/12 of a degree simulation. So that goes that's at the about 6 to 8 kilometer horizontal resolution. So far, really no climate model that runs for hundreds of years is able to run with such resolution. And this shows as a comparison, the top panel here is eddy kinetic energy statistics here from a satellite sea surface height altimetry product, and this is from the ocean simulation. And at some points in a few places, it basically shows the wave number spectrum here to show the scales that are well represented. Importantly, it shows here how basically this oceananigans model basically blows all of the existing other ocean models basically out of the water in terms of its performance, resolution here as a function. Here, usually we compare simulated years per day, per wall clock day. This is a sort of a different metric, slightly different, but it's just simulated years per megawatt hour. So which is also because also about, of course, energy consumption that is, that we begin to worry about. But so the important part here is the way how we leverage the differentiability. So we've been working for the last few years on making sort of this dynamical core also differentiable using a tool called Enzyme, which in itself is a new paradigm. So it's an AD, automatic differentiation tool, that works not at the language level, that actually works on the compiler level, and that makes it immune to immune to the type of programming language that we use. Of course, our focus is on Julia, and because it's on Julia, there also needed to be another tool that's been developed. It's called Reactant, that basically is a pre-optimizer of the language into this multi-level intermediate representation, and it takes care of issues, specific issues for Julia, such as type instabilities and other problems that we are now able that we were able to solve in order to really come up with a dynamical core that we can now use for these hybrid model approaches. And so this has been done we've done this for this ocean model. We've been doing this for an ice sheet model that's been written in Julia, an atmospheric model component as well, but it's not actually the atmospheric model of the Klima effort, but it's an atmospheric model. It's called Speedy Weather, which is a more lightweight atmosphere with a more heavily parametrized atmospheric physics, such as cloud physics. And so so this work is ongoing. So this really is sort of the idea here is the philosophy on how it's a very conservative approach to applying neural network for climate simulations, where we still want to take advantage of the laws that we know very well, namely the conservation laws, but then replacing neural network architectures in parts where the functional representations are neither well known in terms of their structure or well calibrated in terms of their parametric uncertainties. Just as a sort of a sideline also, and it comes back to what I talked about in 2021, is that if you have these gradient information, there's many more ways in which you can use them, such as for Hessian-based uncertainty quantification, reduced order modeling, and optimal experimental design. So maybe I'll stop here and happy to take questions.